Alright, so welcome to the chi-square discussion. We've got some slides that I will go over later, but I want to start with some examples that will work out on the board, because intuitively chi-square is not that difficult, and we'll work out the three major questions that chi-square helps us answer. I'm going to dive right in with an example, and we'll look at some proportions and see how chi-square can help us with that. So suppose we have a proportion. We ask a bunch of Americans, say 100 men, 100 women, we ask them, do you support Donald Trump? And we get information back. We get proportion of men, who's 58% say, yes, I support Donald Trump. We get a proportion of women, 45% say, yes, I support Donald Trump. So, we're back to proportions, and we want to think about what those mean, what sort of conclusions we can make based on that data. And these three questions that I've posed at the bottom. One, are these two proportions statistically different? What I mean by that is, do more men support Donald Trump than women support Donald Trump? Now, looking at the numbers, you would just say, well, yeah, 58% of men support Donald Trump, only 45% of women support Donald Trump. The thing we have to keep in mind, though, is this is just a sample. It's just a sample of 100 men, 100 women. So is that enough for us to say that there's a difference in the proportion of men who support Donald Trump and the proportion of women? So that's the first question. Second question, do these numbers, 58, 45, do they match what we saw on CNN? Or do they match a given set of data that, say, Trump's campaign manager gave us? Does the sample that we conducted, does that data match something else? And then the third question, is gender independent of feelings about Donald Trump? And this is just a variation of the first question. And what we mean by that is, does being a man make you more likely to support Donald Trump? For example, if you were to tell me you have a new friend, and you're telling me about your new friend, and I'm thinking in my back of my head, is your new friend a Donald Trump supporter? I wonder, is your new friend a Donald? It's like the dominant question in my mind. I just want to know if your new friend is a Donald Trump supporter. If I were to ask you, is your new friend a man or a woman? If that were to help me answer the question, is your new friend a Donald Trump supporter, then they would not be independent. If that does not help me answer the question at all, gender is completely independent of whether or not someone supports Donald Trump, then we would say they are independent. And I know it may seem like we're splitting hairs. We're asking, are these proportions statistically different? And is gender independent of feelings about Donald Trump? They essentially are the same question, but sometimes we may need to make a point about independence. Two different variables are unrelated, or sometimes we just may need to say these two proportions are different for whatever reason. So, the three things we'll ask, are these proportions statistically different? We'll call this proportion differences. This second question, does this match a set of data? We'll call goodness of fit. And the third question we will call test for independence. And I'll go over the slides in more detail where it has all that written down, but just to intuitively give you the overview. So, with regard to the first question, are these two proportions statistically different? We already have some tools that we discussed, I think, in Class 2 or Class 3 to answer that question. Remember, we talked about confidence intervals with proportions. Now, if you cast your mind back, we had a standard deviation figure that we used for proportions. It was the standard deviation of the sampling distribution of the sample proportions. And it was this stuff. Right? It gives us the confidence interval. So we might be able to use that and say, all right, we've got 58% is our point estimate. Let's take a look at our sample size. let's build a confidence interval, and let's calculate it. And maybe we'd calculate it from, I don't know, 61 down to 55. We'd say it's somewhere between 55 and 61. And we could do the same thing with women. We could say, all right, well, based on that, it's 48 to 43. And if those confidence intervals don't cross, that might be a clue that they are statistically different. We could do it like that, right? Everyone see what I'm saying? Let me write that on the board. So say men, say is between, what did I say? 55, 61. All right, and women is 42 to 48. Okay, so I've got a, say, a 95, 99% confidence interval that the true proportion of men that support Donald Trump and women that support Donald Trump is between these two figures. That would be pretty strong information to say that they are statistically different, right? Okay, see some nodding. At least no one's shaking their head now. Similarly, we learned this tool for combining two proportions. The standard deviation of the standard deviation of the sampling distribution of proportion differences. Just combine information from one proportion, information from the other proportion, feed in the sample size information, and this would give us a proportional difference. And if this confidence interval did not contain 0, then we would also say, all right, we've got a strong case that these two might be statistically different. So those are ways we could do it. But chi-squared is a way that we're going to learn to do it tonight. And the advantage, Carlos, the advantage of chi-squared is, one, it's a test that's better known. If you say chi-squared, has anyone heard of chi-squared before? Okay, I guess that doesn't help my point too much. All right, in statistical circles, folks will say, oh, yeah, you did the chi-squared test for independence, or you did the chi-squared test for proportional differences, or for goodness of fit, and I demonstrated this or that based on it. So people who know statistics will just kind of nod and say, oh, okay, you did the chi-squared test. That makes sense. That has strong statistical basis. The other thing that chi-squared helps us with is we can use more variables, more groups. If we wanted to do, say, age groups, we could do 5 different age groups, and we could calculate if there's a difference in, 18 to 22-year-olds, whatever the 5 different age groups. Instead of looking at just 2, which we have the tools to do right now, we could look at 5 different age groups, and we could use the chi-squared stuff that way. So, how we're going to approach this is we're going to look at 2 different ways to answer this question. Are proportions statistically different? One different way to answer this goodness of fit question, and one different way to answer independence question. So let's start with the first way that chi-squared help us answer the are these proportionally different question. How we're going to do it is we're going to calculate z-scores for these 2 proportions. We're going to first assume that this entire population of people we asked, 200 people, if we were to take the average, that is an acceptable mean. So that's the first thing we'll do, is we'll take the average of our sample data, and then we'll calculate z-scores for men, z-scores for women. And we'll see, are those z-scores so far away from the average, or away from what we would expect, that we can make a statement about that they are different. So, if we were to pool these proportions, take an average of 58 and 45, what would we get? We would get, what's the average of those 2? Can someone give that to me? 51?
No.
51.5. Okay. 51.5. All right, and then we calculate a z-score for men and a z-score for women. So, all right, so the z-score for men would be the 0.58, 51 would be the 58. 0.58 minus 0.515 divided by the average. We'll call this the pooled. Oh wait, no, I'm sorry. Divided by the standard deviation, which would be this. This standard deviation, sampling distribution of sample proportions. So, based on the pooled average. So it would be, let's see, 0.51 times 1 minus 0.51 divided by 100. That's how many were in our sample size for men. Square root of that. Okay. Let's see. Why don't someone calculate that out for me while I take a breath? Okay, does anyone have the answer to this first one for us? 1.3, I like it. All right, 1.3. And then the z-score for women, we've got a point estimate of 45%, and we subtract that from what we assume to be our mean, which is our pooled average of 51.5%, and we divide that by the standard deviation for this proportion. Wait a minute. Sorry. Standard deviation based on the mean proportion. All right, divide by 100. And I will give you a hint, that is going to come out to negative 1.3. All right, so we've got two z-scores. The chi-squared approach to this involves squaring both of those z-scores and adding them together. So, I'm going to erase this top part, if that's okay. All right, so it's a little x, all right, with a square on it. And if we're talking about our statistic, like our z-stat, we'll put a little stat here, it will equal 1.3 squared plus negative 1.3 squared equals 3.38. Okay, so we've got our test statistic. All we need to do now is take a look at the new distribution of chi-squared and get familiar with that. The degrees of freedom for this new distribution, degrees of freedom, equal k minus 1. And k is the number of groups. So if we have two groups, men and women, it's going to equal 2 minus 1, which equals 1. So we know we're looking for a chi-squared distribution, and we know we're looking for 1 degree of freedom. So let's crack open our textbooks. Take a look at this new distribution. This is, I guess it's not technically the last distribution I will teach you, but the one next week is, I think, easy. All right, the chi-squared distribution is on page 573. Now, you'd be happy to know that this distribution is based on squared numbers, so it's always positive. So you don't have to ask yourself the question, is this a two-tail or one-tail test? It's always going to be positive, and we will look at the area in the extreme tail. So we will look at the area in terms of getting an extreme answer. So let's look at 1 degree, I'm sorry? 573. So let's look at the top line, 1 degree of freedom. And let's scroll our finger over to the right and look at the 0.05 on the area in upper tail. And that would give us that 3.841. Does everyone see that? That would give us a chi-squared critical value for 95% confidence. And I realize I'm throwing a whole lot at you at once, but I wanted to just dive into this example before we break it down too much. So if we were to say, so we've got a test statistic of 3.8, and we've got a critical value, chi-squared critical value, put a little c here, what was it, 3.841. Okay, so what do you think that might tell us? We've got a statistic of 3.38, and we've got a critical value of 3.841. Where do you think I'm going with this? Yes, yes. We're going to set this up just like a hypothesis test, and we're going to say that the value we got from the sample data showed this much deviation, and our measure of what would be extreme deviation would be 3.8 or higher. So let me write that down for us. So suppose I were to do a hypothesis test. Say the null hypothesis is that the proportion of men equals, actually the population proportion, excuse me. The population proportion of men who support Donald Trump is equal to the population proportion of women who support Donald Trump. And the alternative hypothesis is the population men does not equal population women. So in order to answer that question, I would do the chi-squared calculations that we just did. Look at the sample data, look at the sample size. I could find z-scores for men, z-scores for women, square them, add them up, look on the chi-square distribution table, find a critical value of 3.8, and say, the data that we found is not significant enough to reject the null that these proportions are equal. So even though we found in our sample 58% versus 45%, and we thought, oh wow, there's a big difference. Based on this data, we cannot confidently say that there's a difference in these two proportions.
Can you explain why you can't say that? Because the two are different, that's why?
Okay, so these are different based on our sample.
Right.
So we're tempted to say, you know what, more men support Donald Trump than women support Donald Trump. So if you walk around saying that, some statistics student might say, well, how big was your sample size? And you would say, well, 100 men, 100 women. And some statistics student might say, well, what's your confidence level? What's your significance level? And when you start answering those questions, you have to admit that this just may have been pure chance that we got more men saying yes than women saying yes. We cannot say with 95% certainty, based on the chi-square test, that there is a difference between the percentage of men who support Donald Trump and the percentage of women who support Donald Trump. We might be able to say with like 70% certainty, 80% certainty, but we can't say with 95% certainty.
So we reject the null hypothesis.
No, we failed to reject the null hypothesis.
Oh, failed to...
Yep. We failed to reject the null that the proportion, that the true population, this pi sign, this is true population proportion. Remember this, the p with the bar over it, men is the sample, and we found that to be 0.58. And then the p bar over it for women, we found that to be 0.45. So that little p with the bar over it, that's just the sample proportion that we found in our 100 subjects. This pi sign, that's the true population of every American. Does that make sense? Somebody want to explain that a different way for me? Somebody help me out. This is just our hypothesis testing combined with proportion discussion. Take a crack, Amanda? Tell us how we set up this hypothesis test. Tell us the research we did to determine whether or not we could reject this null hypothesis. And then tell us the conclusion that we made.
The true population of men, the population of women is null, and the alternate is that it's 9. And 50 from our sample of 100 men and 100
Let me stop you right there. So the null is that they are equal. That equal numbers of women support Donald Trump compared to men who support Donald Trump. That if we were to do a test like this, we wouldn't, with the true population, we wouldn't get 58-45, we'd get about 50-50. Right? Okay, so that's the hypothesis. And what do we do next, Amanda?
Then we took our sample of 100 men and 100 women.
Yep.
And we got 58% of men and 45% of women.
So why don't we just stop right there and say there's a difference? More men support Donald Trump than women. Can we just stop right there and say we're done? More women? Well, we have 58%.
But it's only a sample.
Okay. It's only a sample. It's only a small sample. All right. So what do we have to do now? Okay. Now what do we have to do?
Alright, somebody else.
All right. So what do we do next? Once we got those numbers,
So you find the chi.
we find the chi-squared. And in this iteration of finding the chi-squared, we started with z-scores, excuse me, and we squared the z-scores and added them together. And we found, all right, 3.38, that's the statistic, that's somewhat unusual, but it's not so unusual that we can say, yes, there's a difference. Okay. Does that make sense? Yes?
So what would be something that is so unusual for your clinical value if you made something?
Well, what if I guess we could do it again so I mean, suppose we had gotten this, 71%. That was our sample. We would do the same process. 71%. We would do the same process. We would find z-scores for this, and this would be a bigger z-score, right? And it would result in a bigger chi-squared statistic, and it would very likely be bigger than our threshold for what is good enough.
So because it's lower than... Okay.
Exactly. Yeah. Okay. All right. Fantastic. So let's move on and answer the exact same question a different way. Let's answer it with table what I guess we'll call a table-based chi-squared test for proportional differences. Table-based test for chi-squared proportional differences. So, this one we got, what did we say? We were at 50. Like, I'm going to need to either get new markers or take my regressions out somewhere else. So 58. And women is, what was it, 45? 45. Okay, so let's put all this in the table, and let's include the other part of the table. No. Total. Alright, and then we're going to compute observed versus expected, and do chi-square this way. So 58 of the men said yes, so that's 42 said no, 45 said yes, that's 55 said yes, total is 100, 100, total here is 200, 58 plus 45 is what? 1 of 3, right?
Yes.
Alright, and 45 is 97? Yes. Okay. 97. Alright, so the first thing we will do when we're doing a chi-squared table-based test for proportional differences is we will calculate the expected value if the null hypothesis is true. So let me erase this. We're still going to have the same question. We're still answering the same thing. We have the null hypothesis that these proportions, the whole population, is the same. Same proportion of men that support Donald Trump, same proportion of women that support Donald Trump. The alternative is they are not the same. So if the null hypothesis were true, what would these numbers have been? And the way we answer that question is we say 103 people said they support Donald Trump. If that is the proportion of supporters for both men and both women, how many men would have said they supported Donald Trump, and how many women would have said they supported Donald Trump? So 103 out of a total 200, that is a percentage that will sound familiar. It's 51.5. Right? So 51.5% of people support Donald Trump under this assumption that these population proportions are the same. And if we asked 100 men, do you support Donald Trump? How many would we expect to say yes? How much?
By 200.
No, we asked 100 men to support, do you support Donald Trump? Let me back up a minute. Okay. If these proportions are the same, 103 people said, yes, I support Donald Trump. That is 51.5% of everyone. Men, women. Of the 100 men we asked, we would expect 51.5 of them to say, yes, I support Donald Trump. Let me write that down and we can absorb that for a minute. So, assuming that these proportions are the same, out of the 103 people that said yes, out of the 100, since 103 people said yes out of 200, we can assume, based on this null hypothesis, that 51.5% of people, both men and women, support Donald Trump. Given the fact that we asked 100 men, we would expect 51.5 of them to say yes, I support. We'll stay on this for a while,
So
until I get some smiles.
of men support.
What's that?
51.5%.
This is our expected, what we would expect to see on our survey, on our sample data.
Predicted
Predicted? Sure. Expected? This is our observed. This is what we would have expected, given the null hypothesis. Let me continue. And like I said, I won't move past this until everyone has a good grip on it, because this is the key point. It's the same here. So out of the 103 people we asked, out of 200 people we asked, 103 said yes, we support Donald Trump. So it says 51.5. We asked 100 women. We would expect 51.5 of them to say yes, I support Donald Trump. Alternatively, it would be the number of men to say, no, I don't support Donald Trump. We would expect that to be 48.5, and we would expect that for women to be 48.5. Okay, so we're gonna, like I said, we'll stay here until we all agree that moving on is a good idea. Question now is, how did we come up with these numbers? The 51.5 here and the 48.5 here. Amanda?
103 divided by 200 times 700.
Yes, 103 divided by 200 times 100. And 103 divided by 200 times 100. It's the column total divided by the grand total times the row total. But the intuition is, we had a total of 97 people who said, no, I don't support Donald Trump. Assuming that half those were men, half those were women, 48 and half of them were men, 48 and half of them were women. If we are to assume that the proportion, the true population proportion is the same, of these 97, half would be men, half would be women. Of this 103, half would be men, half would be women. So which leaves 51.5, 51.5 and I in both boxes. Someone want to explain that to me? Justin?
What percentage of the 200?
Say again?
That's 51%, 51.5% of the total.
Yes.
Where that,
Yes.
where that comes from. So,
Yeah.
Why you divided by the 200?
Now, this does not assume that, half of the people support Donald Trump and half the people don't. There's no discussion about his total support. He could have 70% support, he could have 30% support. All we're saying is it is equal among men and equal among women. So whatever percentage actually support Trump, in our sample, out of the 200 people, there were 103. So that means 51.5% of everybody supported Donald Trump. And if 51.5%, everybody supported Donald Trump, and we are to assume that there's no difference in proportions among men and women, then of the 100 men we asked, 51.5 would say yes. Of the 100 women, 51.5 would also say yes, which leaves the same number that would say no. Okay. Are we good here? We like this? All right. And the second way to calculate the chi-square variable is to take the observed minus the expected squared divided by the observed. And on your slides, which we'll go over later, it's on page 10 on slide 20. That formula is written down. You can reflect on that when we get to it, or you can circle it now. Page 10, slide 20. Or you can just kind of think through how. Do you have a question, Amanda? Oh, sorry. So, all right, so our chi-square for the first one is going to equal our observed point, so we can do 5/8 minus 51.5 squared divided by 51.5. We're going to do that 4 times. We're going to do that for this box, and this box. And we're going to add those all together. And we see if we can make it a team effort. Let me write them out. The second one would be let's do this one. It would be 45 minus 51.5 squared divided by 51.5. Third one is going to be observed. Observed minus expected. 42 minus 48.5 squared divided by 48.5 plus the last one, this box here, is going to be observed 55 minus 48.5 squared divided by 48.5. Okay, so we'll do a team effort here. Can I get one volunteer to do this one? All right, Ishu, one volunteer to do this one. Amanda, one volunteer to do this one. Andre and Takis, can you do this one? Okay. Do I have some numbers? Issue? Which one?
The first one is 0.83. 0.83.
0.83? Anybody else? All right, take your time.
0.82.
Which one? Second one?
Yes, second one.
0.82. Okay. 0.87. All right. 0.87. Okay. Let's add those 3 together. Or add those 4 together.
The first is 82.
This one?
Yeah, 82.
Okay, 82. What do we get if we add all 4 of those together? 3.38. Does that look familiar?
Yeah.
Exact same thing we got last time. So we did it on a table this time. We did it on the z-score method the first time. Our critical value is the same if we were to look in the back of the book. What would it be? It would be 3.8, right? 81? 3.41? 3.841, got it. Okay. What is our conclusion in this question? Null hypothesis, alternative hypothesis? Diana?
Fail to reject.
Fail to reject. Exactly. It's unusual, but it's not so unusual that we're going to say that there is a difference in these proportions.
The number of groups is still just 2, it's just men and women. It doesn't matter if you're taking...
Okay, so we can do it 2 ways. Excellent question. Number of groups still could be considered 2. The degrees of freedom for a table-based test is, let's see, degrees of freedom, F, equals our column minus 1 times row minus 1. So we have 2 columns and 2 rows. So that's going to equal 2 minus 1 times 2 minus 1 equals 1.
So it's not. But it can also be k minus 1.
We could, as long as we remember that if we were just to do this on z-score methods, then it would be 2 groups. If we put it in a table, and we're going to expand this. Remember I said the beauty of the chi-square test is we can do more than 2 groups. We can do multiple groups. We have multiple cells. And this will always work. Columns minus 1 times rows minus 1.
So we could do yes, no, or unsure.
I guess we could do. Yeah, we could. Yes, no, unsure. Men, women, transgender. Do age groups might be a little easier to calculate. Okay. So we have done everything we need to do to answer the second 2 questions as well. The next is goodness of fit. All right? Does this match what we saw on CNN? We'll call that a goodness of fit test. That would be a situation where we could make the null hypothesis whatever we desire. We could say the proportion of men equals, we see on CNN, the proportion of men who support Donald Trump is 61, and the proportion of women who support Donald Trump is 48.48. The null hypothesis is that the proportion of men does not equal 61, or the proportion of women does not equal 48. It could be even. We could say, it's just even. The proportion is 50% of men, 50% of women. And then the alternative would be no. What you say is not true. We did a goodness of fit test with the chi-squared statistic, and we found an unusually high chi-squared statistic. So we are going to reject your goodness of fit. The last question, this question of independence, let's see. Null hypothesis, gender, and feelings about Trump. Trump are independent. Okay, the alternative is that gender and feelings about Trump are not independent. And recall, what are we saying? We're saying feelings about Trump and gender and feelings about Trump are independent. What are we saying in that case? What we're saying is that being a man or being a woman has no effect, in terms of our ability to predict whether or not you're going to support Donald Trump. The alternative is knowing whether you're a man or a woman helps us to predict whether or not you will support Donald Trump. And we will calculate this from a chi-square perspective the same way. We will assume that the proportion, the numbers, everything is the exact same thing that we just went through. We will assume that of the 103 people who supported Donald Trump, we'll assume half of them are men, half of them are women. Because we are assuming gender and feelings about Trump are independent. They have no predictive ability. We have no predictive ability if we know.
So we reject.
Oh, could we reject based on this analysis? So we're going to assume that they're independent. All right, and we're going to set up a table like this with observed and expected. And we're going to calculate a chi-squared statistic for this information. And we're going to do that observed minus expected squared divided by expected. We're going to do that 4 times. We're going to add them all together. And we're going to come up with 3.4, right? And we're going to look in the back of our book, the chi-square. We would fail to reject. We would fail to reject this null hypothesis.
Okay, for the second one, it's said that we reject, right?
No, for none of them, we didn't reject for any of them.
Oh, I heard that.
Okay.
Oh, okay.
So we just did 4 things. The first was, we said, let's look at proportional differences using a z-squared method. And if these are z-score, you're going to have to keep me honest here, using a z-score method. And if these z-scores squared add up to a significant chi-squared statistic, then we're going to say that's unusual. The second thing we did is we answered the same question. We did a chi-squared test for proportional differences, but we did it with a table. And we calculated some expected frequencies. We compared that to our observed frequencies. We took expected minus observed minus expected squared divided by expected, added up all 4 cells, used the appropriate number of degrees of freedom, which was the same, and we failed to reject the null hypothesis. So the first 2 things we did, we tested, are these proportions the same or are they different? We did that first with z-scores, second with a table-based test. Second question we asked, goodness of fit question. Does this match the data that we have? Does this match what our advertising people are telling us? And that could be anything. In this example, if we wanted to use these exact numbers, maybe that's where you caught me. If we wanted to use these exact numbers, if we wanted to say proportion of men equals 0.50, proportion of women equals 0.50, and the alternative is that the proportion of men does not equal 0.50, and the proportion of men does not equal 0.50. In that case, we would use the exact same numbers, get the exact same result. But this goodness of fit test, it doesn't have to be those same numbers. It could be whatever we see on CNN, whatever the claim is being made. We calculate the expected based on whatever your claim is, compare that to observed, calculate the chi-squared variable. And then the last thing we did was a test for independence. Done the exact same way mathematically. Any questions? Yeah?
So for the second part, the number will change the on CNN.
Say it again?
The number will change. Like they have right now 58 men for 58 says yes, 58 says no. So does it match what we saw on CNN? Will the number change? Percentage?
Oh, okay. So, well, if CNN says 50-50, then that's the test we already ran. And we cannot reject what CNN says based on this data. CNN says 50-50, but we got a little more variation than that, but not so much that we can say CNN was wrong. CNN didn't have to say 50-50. CNN could say whatever they want, and we would change our numbers based on that.
So the number we're changing is the number at the bottom,
Number we're changing.
right? We're doing the test for the second part.
For the goodness of fit. We change it. Oh, yes. Sorry.
Yeah. So
Yes. Yeah, okay. So suppose CNN said, alright, suppose CNN proportion of men that support is 60, and proportion of women that support is 40. Alright. 60 or 40. Okay, so you're right. So now, if we were to run this test, we need to change these red numbers. So, out of the 103 people who said, yes, I support Donald Trump, we expect, all right, so 103 people said, yes, I support Donald Trump. All right, we expect 60% of men to say yes. So, wait a minute. I'm going to confuse myself here.
Oh, I think you have
Oh,
66.
Well, our numbers would be the same. It was 60. Yeah, so it would be 60. It would be
Just
60.
change 60.
It would be 60% of the 103, and it would be making myself dizzy here. Somebody help me out. And Randy, let's come back to this.
Yes, it's 60%. You have to change the whole. You have to change the whole expected. Sorry, you have to change the whole.
Yes.
Numbers. You have to put that,
Yes.
60,
Yes. I'm not going to attempt to crank it out right now.
yeah.
Let's go through the slides and maybe see some other examples and have all this information that I just kind of threw at you just neatly on the slides. But the good news is this is everything for tonight.
Oh.
The slides are just to reinforce these examples. Yes?
Since we have to answer 3 questions, are there not always the same answer? Like for some you might reject and others you might fail to reject, or is it always the same for all 3? Like, because it looks like we got the same answer for all 3 of them, fail to reject, but is that always the case, or is that just in this instant?
Okay, well, it's just this instance, especially because we asked the same question, used the same numbers each time.
Okay.
We could have, based on this answer, answered this question and answered this question, assuming CNN says 50-50, and assuming we want to know if there's independence.
So
So-
sometimes you will be provided different data for each question.
Yes,
Okay.
yes. I hope, and hopefully, maybe give me some feedback at the end of class. I hope I didn't confuse you by using the same example for each one, but the point I wanted to make is that it's all the same. Is that all 3 of these things can be calculated the same way. The numbers will be different, and of course there'll be examples where we reject or fail to reject. But actually, in answer to the question I think you're asking, if the numbers are the same, then the answer will be the same.
Okay.
Yes.
So, the chi-square method is used to calculate proportional differences or something.
It could be. Could calculate proportional differences. Are these proportions different? It could also be used to calculate goodness of fit. Is the number accurate based on our sample? It could be also used to calculate are 2 things, 2 variables, independent. Okay. I want to keep going. Are we okay to keep going? What time is it? Let's 7:35. Okay. Let's keep going and see how this feels. chi-square test. All right, is population proportion 1 the same as population proportion 2, same as population proportion 2? We did chi-square test for differences in population proportions. We did it 2 ways. First with z-scores, and then with our observed versus expected table. Second thing we did was goodness of fit. Third thing we did, test for independence. All right. Sum of squared normal deviance, z-scores. Let's see, the shape depends on the degrees of freedom. All right. The mean of this chi-square test is equal to the degrees of freedom. So if we have 2 variables, 2 groups, 1 degree of freedom, we would expect our ratio to be 1. Right? The number expected versus non-expected divided by our base z-score, our base mean, would be 1. Right? If we have more variables than that, then we expect the chi-square number to be higher. Right. I mentioned that the chi-square distribution is always positive, so we only have to worry about what's in the upper tail. We don't have to ask ourselves, is this a 1-tail or 2-tail question? We check degrees of freedom and we say, all right, our mean is here. What is so unusual that it would be in the extreme upper 5% tail of the chi-square distribution? Okay, the chi-square distribution. Okay, the first thing we did was we tested to see if multiple populations are the same. We have a null hypothesis. We said population proportion of men that support Donald Trump is the same as population percentage of women who support Donald Trump. We could have different categories. We could have multiple categories. We would test the null hypothesis that they're all the same, and then we would look, based on our sample data, did we find a chi-squared statistic that is so unusual that we reject that and say that they're not all the same. All right. Remember, the first way we did this was with z-scores. We said, let's calculate based on our test statistic divided by what we decided was the pool population proportion. We said we have 103 people who said, yes, I support Donald Trump. All right, our pooled percentage would be 51.5%. And we divided that by what we know to be the standard deviation metric based on a few classes ago for the standard deviation of the sampling distribution and sample proportions. Same thing here, just where this proportion is the common pooled population proportion. And this was just a weighted average. We just had 2 men and women, and we took an average and we calculated that the average proportion is 51.5%. If we had more, we would have to do a few more intense calculations, but it would still be the same. Let's do an average. Alright, and then remember we got the z-scores for each individual statistic, and we added them, and we squared them, and we added them up. Steps. Alright, first, for the chi-square test for proportional differences, pool the sample proportions, compute each sample z-score, calculate the chi-squared value by adding them all together, apply the decision rule. If this chi-squared stat we got is bigger than the critical value, reject the no difference null hypothesis. In our example, we came up with 3.4, critical value of 3.8, so we did not reject. We could also use p-values to make this decision. And when you do some Excel work, you will calculate how to do a p-value. And I'll try to find that Excel example and make sure you do that one, but I'll see if I can find some others that you don't have to do. Because I've gotten some complaints that Excel homework is too long. But it is important you calculate how to do a chi-square and how to get a p-value on Excel. P-value and critical value have the inverse opposite relationship. The critical value says, right, if the test statistic is so far beyond that, then that is unusual. It's so unusual that it happens a very low percentage of the time. So, if we find an unusually high chi-square value, we will find a very low p-value. And if our p-value is lower than our significance level, then we can also reject the null hypothesis. Recall we said degrees of freedom in this first example is k minus 1, where k is number of groups. All right, so that's the first thing we did. Second thing we did is said, well, let's put this in a table. Let's do some calculations that way. But before we do that, let's do this example. So we're going to stay on the first one. We're going to do the z-score one again, and we're going to do an example based on the z-score method. So, Alvarez Communications has just received 3 shipments of cell phone shells that it uses in its assembly process. Each shipment is from a different supplier. You want to test the proposition that the proportion of defective shells is the same for all 3 shipments. So you randomly select 200 shells from each shipment and find the following defectives. Alright, so from shipment 1 you find 6 defectives, shipment 2 you find 26, shipment 3 you find 22. Conduct the proper hypothesis test using the significance level of 5%. So when you see these numbers, maybe your first thought is, gosh, I'm never going to use the supplier that sent me shipment 2 or shipment 3, because look at all the defectives there, right? All right, so why would you not immediately jump to that conclusion? It's just a sample, right? So let's do a chi-square test. Let's find a z-score for all 3 of those. Let's square it, let's add it up, and let's see if that is enough information for us to say that there's a significant difference between these 3 population proportions. So our hypothesis is that the supplier 1 is the same, proportion of defective rates is the same for supplier 1, supplier 2, and supplier 3. And we will assume that. We'll see if we get overwhelming evidence to the contrary. Not all of these are the same. So remember, in shipment 1 we had 6 defectives out of 200, 3%. In shipment 2 we had 26 defectives out of 200, that's 13%. In proportion 3 we had 22 defectives out of 200, that's 11%. Take a weighted average of that, and we find 9%, total of 54 out of the 600 shells we received were defective. That came out to 9% of the total 600. So our null hypothesis is that all of these are 9% defective rate. But we know from our sample that it didn't quite come out to 9%. But the question is it unusual enough? So let's do the chi-square test. Recall the first one, we had a very low 6 defectives, so that's 3%. The second one was 26, so that's 13%. The third one was 22 defectives out of 200, that's 11%. Minus our assumed mean for all 3 populations, divided by what our metric is for standard deviation, sampling distribution of the sample proportions. And we come out with a z-score of negative 2.97, 1.98, 99. Now just think about these z-scores for a minute. Negative 2.97. This is back to class 1, where I drew the normal distribution, and I said 95% of the samples would be within 1.96 standard deviations. And I think I said 68.3% would be within 1 standard deviation. And this is a z-score of almost 3. So that may trigger some alarm bells right there. You might say, gosh, all right, that's a little unusual. Let's keep that in the back of our mind. This other shipment seems a little unusual too, based on our assumption that everything is the same. So we square those 3, we add them up, and we get a test statistic, a chi-squared stat, of 13.67. Next thing we do is we look in the back of the book, chi-squared, k minus 1. We have 3 groups. So 3 minus 1 is 2 degrees of freedom. What were we looking for? 95% confidence interval? Or 95% significance level? Right on. 5.991. And our chi-squared statistic was 13.67. We say that is so unusual, we reject the hypothesis that everything is the same. Make sense? Right. Reject. P-value version, when you do it on Excel, would be a very, very low p-value version. 1/10 of 1%. That's the chances of something that unusual happening. Summary of procedures. Oh yeah. Now we're on to the test. All right. Now we're going to put this in a table, and we're going to ask ourselves. All right. So we're done with the Alvarez example. We're done with calculation 1, which is looking at z-scores and adding those all up. Now we're on to the second way to calculate the chi-squared metric, which is to put them all in a table. Calculate the difference between observed and expected. Add those up, use the appropriate number of degrees of freedom. Look at the critical value in the back of the book. See how unusual your statistic looks. So we show a table of observed sample frequencies, build a table of expected sample frequencies, which I think took some minute to comprehend, but I think that's going to sink in if it hasn't already. Calculate chi-squared, apply the decision rule. Degrees of freedom, remember rows minus 1 times column minus 1. We can do huge number of rows, huge number of columns. That's the beauty of the chi-squared. We're not limited to just 2 groups. And then we add them up. And sorry about this. You can see there's like 2. You can see there's a superimposed sum sign there. The reason for that is the slides that the textbook uses. It's weird when I upload them on my Mac, so I have to like input them on. But when I'm back on a PC, I see like the stuff I inputted on and the stuff that was there before. So everything's right on your slides. But it's just the sum of everything. Observed minus expected. That's not equals. That's observed minus expected. That's just the minus sign that I pasted on because it wasn't there when I opened it on my Mac. Divided by the expected frequency. Okay. Let's do this. I guess we're not done with the Alvarez communications example. Let's do the same one in a table-based format. Remember we had 3 shipments. Shipment 1, shipment 2, shipment 3. 6 defectives, 26 defectives, 22 defectives. So let's think about what our expected values would be if all these population proportions were the same. So out of a batch of 600, 54 of them were defective. So that's about 1/12, right? So 54 divided by 600 is about 1/12. It is specifically 9%, which we saw earlier. But just so we have the intuition, about 1/12 of our total shipments were defective. So out of 200 from retailer 1, we would expect about 1/12 of these to be defective, or 9%. So we would take 9% of 200, and we would get 18. So you'll see in a minute, I think there's a slide that actually says this. This is the column total divided by the grand total times the row total. But the intuition is 54 out of 600 were defective, so out of the 200 in shipment 1, 1/12, about 9% would be, that's what we would expect to see. Our next slide. Column total divided by grand total times row total. And we calculate the expected frequency for each one would be 18 because they're all the same. They each had 200. Now these don't have to be, the reason these are all the same is because the shipment sizes were the same. If this were 300, then it would be different. Observed, expected in each cell. And we do the same calculation we did a moment ago with our Trump example. Observed minus expected squared divided by expected. We do that 6 times. Add them all up. Degrees of freedom is rho minus 1 times columns minus 1. Gives us the same critical value, 5.9, and gives us the same, and all summing up those gives us the same test this statistic, 13.67. Any questions? All right. Goodness of fit. We're on to the third thing. But we happily know that the math is exactly the same. It's just asking a different question. Distribution can be used to conduct the goodness of fit to determine whether sample data fits a particular model or distribution. That's just the fancy way of saying it's what CNN told us. It's what HR told us. It's what our account representative claimed. Let's do a sample and see if it comes out the same. You can see the chi-squared statistic is based on the same math. Again, that is not an equal sign. Sorry, that is a minus sign. How's everyone doing? Do you want to take a couple minutes or keep going? Keep going. What are we at 7 for? Let's keep going. We got maybe 30 minutes left, probably. All right. So, okay. Formula is the same. Let's look at an example. All right, M&M's, Mars candy. Mars candy has different proportions for blue, brown, red, orange, green M&Ms. So I hate it when my M&M's bag is short of red M&Ms. Nothing makes me angry. They make a variety of these candies, 6 different colors, and if you look on the Mars website, perhaps, I haven't checked, but you might find them claim that 24% are brown, 13% are red, 13% are yellow, 14% orange, 20%, whatever those numbers are. So you take a random sample of 268 individual candies, 15 small bags, and you calculated some observed. So below are the sample counts. Okay, so these are your sample counts. In your sample of 268, you found these numbers. So you're going to do a goodness of fit test with these numbers. So your null hypothesis is we're going to believe what Mars says is true. They claim 24% blue, yada, 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 yada. All of those. That's what they claim. We're going to say the alternative is that that is not true. So, out of our sample, we're going to do observed minus expected squared divided by expected. And we're going to add all those up. So our expected frequencies, based on what Mars says, were these numbers. Now, they did not put this example in a table, but that's fine. We can look at them individually. So for the blue, we expected, out of our sample of 268, we expected 64.3 blue M&Ms. What we actually had was 54. So we only had 54 blue M&Ms, and we were expecting 64. So let's take 54 minus 64, observed minus expected squared, divided by expected. Let's do that 6 times. Let's add it up. And we get a chi-squared statistic of 5.5. Degrees of freedom, we have 6 groups. 6 minus 1, 5 degrees of freedom. Now, I don't know if you remember, I kind of rushed through the first slide, but the average, the mean on a chi-squared distribution is the number of degrees of freedom. So if we have 5 degrees of freedom, we would expect the average chi-squared statistic to be 5. And the one we came up with in our sample is 5.5. So you might say, oh, it's a little unusual. But just eyeballing it, we think, if the average is 5 and we come up with 5.5, it's probably not that unusual. But let's look in the back of the book just to make sure. Let's look with 6 degrees of freedom. We would calculate, if you were looking in the back of your book, 6 degrees of freedom, the critical value would be 11.7. 5 degrees, sorry, 5 degrees. Apologize. Thank you for catching me. So 5 degrees of freedom, we would need to see a chi-squared statistic of higher than 11.7 before we were to file claim against Mars M&M's candies. We might be a little annoyed because we got unlucky. We were shorted reds. But we can't say that the true population proportion of reds is lower than they claim on their website, unless we were to find a statistic greater than 11. But we found 5.5. Can't reject. Given the sample data, we can't reject the claim that proportions of M&M plain melt chocolate candies are different than stated by the company. We can't reject the claim that the proportions. We can't reject the claim that they're wrong. All right, makes sense?
Yes.
All right, our last thing to do is a test for independence. Are two things related? Now we've got a summary of the goodness of fit. Degrees of freedom, as we talked about. Go through those steps as we just went through. All right, test for independence. Are two factors independent of each other? We're going to put this on a table. We're going to calculate observed versus expected. We're going to set up a hypothesis test. And we're going to say the factors are independent. They have no relationship to each other. Whether someone is a man or a woman gives us no predictive ability about whether or not they will vote for Donald Trump. And if we find something that contradicts that in such an unusual fashion, we're going to say, you know what, they are actually correlated. The newscaster can say more men support Donald Trump than women who support Donald Trump. Okay, so there's a note that each cell, for example, each cell needs to have a minimum of 5 in it in order to make the chi-squared relevant. We'll look at examples that have more than 5, but make a note of that if you're trying to do this at work for something unusual that has a small frequency in one particular cell. Same thing. We're going to calculate expected values, column total, divided by grand total times row total. Same process we went through with 103 people support Donald Trump. All right, out of the 100 that we asked, we would expect 51.5 to say yes. And the chi-squared test statistic is done the same way. The sum of observed minus expected divided by expected. Show the table of observed, show the table of expected, compute chi-squared, apply the decision rule. And of course, degrees of freedom when we put on any table, row minus 1 times column minus 1. All right, let's look at an example. Badon University. So this table shows grades for a random sample of business statistics students at Badon University over the past 5 years, along with a measure of class attendance. We want to test the hypothesis that student grade and class attendance are independent. So what does that mean if student grade and class attendance are independent? I can tell you, I'll give you a hint. I'm not going to like the answer. Brandon. Yeah, it doesn't matter if you come to class. It won't affect your grade. It means you're not learning anything in class, perhaps. So we know that's not true. But, right. This is a different university, Badon University. So maybe it's true there. So we've got some data. We've got students who got A's, B's, C's, and D's. Now let's direct our attention to the bottom row. Over the past 5 years, whatever, 340 students have got A's, 265 have got B's, 220 C's, 175 D's out of the 1,000 students in this sample. Now, in this row, we've got students who missed 3 or more classes, or 3 or fewer classes. So 1, 2, or 3 classes, all right? So they have pretty good attendance. These students missed 4 or more classes. So let's just take a look at the data to start with. The students who got A's. So we have 160 students who had good attendance and got A's, and we had 180 students with bad attendance and got A's. Now, this 180 is obviously more than 160, but let's direct our attention to the total number of students in these 2 categories. So the total number of students with good attendance was 460. Total number of students with bad attendance, 540. So there are a larger pool of students who had bad attendance. So we naturally might expect, because there's a larger pool of students, that there would be a larger number who got A's. Question is it large enough to account for that difference, or can we claim some lack of independence? So let's go through our process. Let's set the null hypothesis. Grade is independent of attendance. No relationship whatsoever. Alternatively, if we find enough information to reject that, we'll say grade is not dependent. That coming to class actually affects your grade because you learn more. That's what this alternative hypothesis is saying. So let's do the expected frequencies. So recall we have 340 students who got A's out of a total of 1,000. So we had 34% of students got A's. So out of a pool of 460, we would expect 34% of those to get A's. So 34% times 460 is going to give us 156. 34% of 540 is going to give us 183. Same thing down the line. These are our expected frequencies. So notice we expect a few more bad attendance. We expect a few more bad attendance A's than we do of good attendance A's, given our null hypothesis that these are completely independent. But we're going to see if we have enough to say that there is actual dependence there. So we've got observed, expected, observed, expected, observed, expected, observed, yada, yada, yada. So we just go through each one. Observed minus expected divided by expected. We do that 8 times. Observed minus expected squared, divided by expected. Add those all up. What's our degrees of freedom here? 7. All right, somebody walk me through, how do we do this degrees of freedom calculation? What? 2? Yeah. So you get 2 minus 1. That's right, Selena. Times 4 minus 1 is going to be 1 times 3. 1 times 3 is 3. We do the whole observed minus expected squared divided by expected. Add that up 8 times, and we're going to come up with a chi-squared statistic of 1. And we're going to check in the back of the textbook for a chi-squared critical value of 5% significance, 3 degrees of freedom. And we're going to get 7.8. Is that right, Amanda? So what do we do with that information? We've got critical value of 7.8, and we've got a test statistic of 1.02. What's that?
Can't reject.
We cannot reject.
Yeah.
Right? We cannot reject the null hypothesis. And our null hypothesis was assuming independence, right? Right? So let's go. So what that means is that in this class, in this school,
Whatever.
it didn't matter
Yeah.
if you went to class. You didn't necessarily get a better grade.
What's that class?
But but just let's think this through, just 1 second, all right, before we decide we don't have to come with class. So we observed 160 A's in this good student population, and we expected 156. So we got a few more, right? All right, and in this bad student attendance, we expected. We observed 180, and we expected 183. So we got a little fewer than we expected, right? So if we really want to find a way to fudge the numbers, all we have to do is lower the significance level, or increase lower the confidence level to maybe 70%, 60%, something like that. And then we might be able to say that coming to class is related. All right, but based on what we found, we cannot make that assumption. Any questions? All right, are you feeling good?
Yeah.
All right, good. Everyone feeling good? So, all right. So now that we finished this class, did it help, or was it confusing that I went through that lengthy example at the beginning?
I think it was better to go ahead and just dive right into it and
Good.
kind of explain what was going on and what you showed us.
Good. All right, thank you. I'll be here if you have any questions on quizzes or anything like that. Otherwise, I look forward to seeing you next week. Yes,
So what's the assignment this week?
Oh, the assignment's just your regular homework, and then there'll be a quiz. But I did get some feedback that the Excel problems are too long, so I will look at
I
those.
think part of that is just that the pressure requires so much inputting that it really is like you spend more time putting it in than you are like trying to digest what you're doing.
Okay.
So That's where I think what we were saying when we referred to as sell out.
Oh, okay. I don't want to put you in hell. But yeah, so stand by from an email saying, okay, these go.
I spent like 2 hours putting
Yeah,
this
no,
stuff in.
5 hours.
Oh, sure. Yeah, let me set the clock here.